This video is on free energy and how it relates to the equilibrium constant K. Also how to calculate delta G when we have non-standard conditions. Okay, so two more ways to use free energy to analyze reactions. So one way is that we're now going to learn that we can use delta G at standard conditions to help us calculate delta G at non-standard conditions. And we'll talk in just a minute about specifically what those conditions are and how we can go about calculating delta G in a non-standard situation. And the second one is we can relate the values of delta G and the equilibrium constant K for a reaction. Okay, so free energy under non-standard conditions. So when we talk about calculating delta G using the sum of the products minus the reactant, so P minus R, and using our table of all the delta G values, those are at standard conditions, which if you look at that sheet, it says 298 Kelvin at the top of the paper. So for the first thing is, what if it's not at 298 Kelvin? Well, then
Brady Simmons, please report.
Then I cannot use the delta G values because the conditions aren't for that situation. And there are other values other than temperature that affect this. So we'll talk about that. So the first point is that most reactions actually occur under non-standard conditions. And so standard conditions is more than just the temp, okay? Standard conditions are the concentrations of all reactants and products equal to 1 molar, or the partial pressures equal to 1 atmosphere, and a temp of 298 Kelvin. So if that's not the case, if a reaction is occurring and it doesn't meet one of those conditions, then it's at non-standard conditions, and I cannot use the delta G values that are on that packet that we work with. Okay, so instead I have to use a new formula, and it's a formula that relates this delta G under non-standard conditions. Notice it doesn't have the not symbol up at the top because it's not a standard condition, and it relates it with delta G at standard conditions. Okay, and so that formula is that delta G at any conditions, it can be calculated if I know delta G at standard conditions, if I know R, which is the gas constant, T, temperature, and the natural log of Q, which of course is our reaction quotient, or we call it fake K. So R is the gas constant with slightly different units here. T is temp in Kelvin, and Q is the reaction quotient, or my idea of a fake K. So if I have all of those pieces of information, then I can calculate a delta G value for a reaction that's occurring at non-standard conditions. So let's do a practice, and hopefully this will make that equation make sense. All right, so calculate delta G at 298 Kelvin for a mixture of 1 atm of N2, 3 atms of H2, and 0.5 atm of NH3. So this is not at standard conditions. They're not all 1 atm. And so I can't just look up the values in the chart. However, I can look up the values in the chart. Oh, it gave me the reaction that I didn't write. Sorry. I can look up in the chart delta G at standard conditions. And so I can solve this P minus R using the chart. So I go and I look up NH3, there's 2 moles of it, and its delta G value is negative 16.66. I subtract from that the delta G's of my product, reactants, but guess what? They're elements, diatomics, in their standard state, and so they're all going to be 0. And so delta G at standard conditions is negative 33.2. 0.32 kilojoules. And if I'm going to use this formula that we just talked about, I have R, I have T, I just calculated this, I need Q. So the next thing we need to calculate is the Q value, which remember is written like K, so the partial pressure of my products raised to their coefficient over my reactants. I plug in my numbers. And we get a Q that is quite small. Remember, Q, just like K, is unitless. And now all of a sudden I have all the pieces of information for my problem. So I have that delta G is equal to delta G at standard conditions plus RT times the natural log of Q. Delta G at standard conditions is negative 33.32 kilojoules. Plus RT times the natural log of Q. Careful with your R here. I gave you R in joules, but we are dealing with delta G in kilojoules, so I would change that. So this is kilojoules per Kelvin mole times T, 298, times, I'm out of room, the natural log of Q, which I just determined. If we do all of that, we get a delta G value of negative 44.9 kilojoules for this reaction that's occurring at non-standard conditions. So that's how you can use Q. You can use delta G at standard conditions to calculate delta G at non-standard conditions. Okay? And then the second part of this discussion is the relationship between delta G and K. So here's my formula that we've been working with. Let's talk about a couple things. So we have learned that at equilibrium, Q is equal to 0. And, oh my gosh, I'm sorry, delta G, is equal to 0. So sorry. And Q is equal to K. Wow. Okay, so substituting that into this problem, it gives me 0 is equal to delta G at standard conditions plus RT times the ln of K at equilibrium, right? With a slight rearrangement to solve this for delta G, taking RT ln of K to the other side by subtracting it, I end up with this formula, which is on your cheat sheet for the AP Chem exam. So just a couple things to talk about here, which is how we can relate delta G and K. So if delta G is negative, that means we have a spontaneous reaction. And it's proceeding, left to right, creating lots and lots of products. And so my equilibrium constant, K, is going to be quite large. It's going to be much greater than 1. You should be able to rationalize that because, like we said, if it's spontaneous, it's moving in the forward direction and you're getting lots and lots of products. And remember that K is a ratio of P to R. So my products are way larger than my reactants. The reverse is true if I say, if delta G is positive, reaction is non-spontaneous, and the K value for that situation would be much less than 1. And then if delta G is 0, the K value is actually going to be equal to 1, and that's fairly easy to prove to yourself by plugging this into this formula up here, and I'll show you that. So this is kind of the important relationship. This last one, let's talk about it for a second. If K is 1, well, the natural log of 1 is 0, and so then 0 times R and T is 0, which means delta G is going to be 0. So just something to think about, that you can determine that mathematically by looking at the equation. And then how can we use this? Well, we can use it in a problem like this to actually calculate the equilibrium constant. So the standard free energy change for the reaction below was previously calculated. They give me delta G at standard conditions. And they say use this value to calculate the equilibrium constant. So back up here to this new reaction that I have, or formula, sorry. So I know that delta G is equal to negative RT times the ln of K, and I'm looking for K. So get R and T off of that side, and that's going to leave me with the natural log of K equal to delta G over negative RT. And to get rid of a natural log, hopefully you know this, that you raise both sides to the E. And that's going to cancel your negative log. So we end up with K equals E to the negative delta G over RT. And from here, we're just going to plug in our numbers. And remember that E is just a button on your calculator. So this whole value, right, is going to be the negative of it. So I just pulled the negative out in front. Delta G, they gave to me negative 33.3 kilojoules per mole. Same situation here with R, that we want it in kilojoules, so 0.00831 kilojoules per Kelvin mole. And then times T, which was 25 degrees Celsius, so 298 Kelvin. Right, check out your units. Everything cancels, which hopefully sits okay with you because K is a unitless number. And then I end up with K equals E to the negative some number, right? This value up here is just a number. And I did not do that, so let me do that real quick. So I ended up with negative 13.447. And then all you have to do is hit the button on your calculator. Raise E to the negative of a negative, so it's going to be positive. And I got something like actually, hold on. Having a calculator error. Give me 1 second. Yeah, like 6.92 times 10 to the 5th. So this is a huge value of K. But again, stop and think about this. That makes sense. This reaction is spontaneous. It's proceeding in the forward direction. So my ratio of products to reactants is going to be quite large, and I would expect K to be large. Something interesting, we talked about this in class, okay? And this ties everything together. It's not on this paper, but it's worth a couple minutes of our time. All right, I know this reaction is, I know delta G is negative. And so let me erase part of this where I can write somewhere. Okay. So I know that delta G is negative. And I would like for you to tell me what you know about delta S and delta H. So think about that for just a second, and then we will have a discussion. Or pause this video and think about it so that then we can discuss. Okay, so delta S is the easier component of this to think about. So this is an all-gas reaction, so I should be considering moles of gas. I start with 4 moles and I end up with 2 moles. So I have a decrease in entropy, and delta S should be negative. I don't know the value without doing any calculations, but that's not what I'm getting at. So then at this step, I want to know what you know about delta H. Okay, and this brings it all together from our discussion of what drives a reaction toward being thermodynamically favorable, okay, or spontaneous. So we learned yesterday that a negative value for delta S does not favor spontaneity. So delta S is doing this reaction no favors in driving it toward being spontaneous. However, delta G is still negative, and it is spontaneous, which means it must be carried by enthalpy. So delta H in this reaction must be the one who is pushing this reaction toward being spontaneous, and the only value that delta H can be to favor spontaneity is negative. So this reaction, it must be exothermic because this is an enthalpy-driven reaction. Because this reaction is spontaneous, one of the two has to carry it at least. It's not entropy, and so it must be an enthalpy-driven